Hey grapplers, welcome back to episode 9 of our Golang series, where we will unravel the mysteries of Go programming. Today we are diving into data types, the foundation of any programming language. We will explore every hidden tip, trick, and secrets you need to know, along with real world examples. Whether you're a beginner or a seasoned coder, this episode is packed with essential tips, tricks, and real world examples. You don't want to miss. So let's dive in. First things first, what exactly is a data type? Simply put, a data type tells the compiler what kind of data a variable will store. Okay. It's like deciding what kind of container to use for your groceries. For example, if you're trying to buy veggies, you'll be using plastic bags to store it. And if you're trying to buy liquids, you'll use something called as glass jars to store it, and so on. So think about filling a water bottle. You can't put oranges in it, right? That's because the bottle is designed for liquids but not for solids. Similarly, in programming, you must choose the right type of container, that is, the right type of data type for your data. It's like picking the right container for your items, like we have buckets for water, jars for jam, and so on. So, Golang's data type fall into three categories: basic, composite, and reference types. We will start with basic types like integers, floating points, strings, and booleans, and then we'll uncover the deeper technical details, including the ranges and special cases. And later in further coming sessions, we will discuss about composite and reference types too. So, integers. What are these integers? Integers are nothing but the whole numbers. That means it can contain like negative numbers, zero, and positive numbers. Okay. So Golang provides both signed and unsigned integers. Okay. First we'll see about integers. How to declare a variable. Var a. And now we are just telling that this is of type int and will store a value a. And let me print this out, and you can see the output as 12. Okay, so we have told the compiler that, hey compiler, this a variable is of type int and it is storing value 12. So we are statically typing the type of the data which we are storing in a. Okay, so that is how we can define the data type of the data we are trying to store in a variable. And now this particular integer is further divided into two subtypes. Like we have signed integers and we have unsigned integers. And what are these two? Signed integers can hold both negative and positive numbers. Okay. And the range is determined by 2's complement representation. So what is this range? See, for any data type, range is nothing but the minimum value and the maximum value. The the number of values, like how much, like how big a number you can store. So what kind of minimum value you can store in a particular data type. So that is what a range. Okay. So and this range is calculated using 2's complement representation, and we do even have a formula. So we have a range formula. Okay. And that is nothing but, and it is different for signed integers as well as unsigned integers. So for signed integers, the minimum value and the maximum value, that is the range, can be calculated using a formula minus 2 power n minus 1 to 2 power n minus 1 minus 1. And this extra minus 1 is because of 0. Okay, so using this formula, you can calculate the range, so the minimum value and the maximum value of the data type. Okay, let us see for example. This is, we are storing an integer, right? So yeah, before going into that, let us discuss about subtypes. And even we have even more like further divided subtypes in integers also. Like we have int 8, int 16, int 32, int 64. And what are these? These are the specific versions of integer types that define how much memory they use and the range of values they can hold. Okay, for example, int 8 uses 8 bits of your memory and can store numbers from minus 128 to 127, which is being calculated by the range formula which we have told before. So while int 16 uses 16 bits of the memory and has a larger range. So these subtypes help us save memory and ensure better performance based on the needs of your program. Okay, so let us see that. First, we'll discuss about signed integers. As you can see over here, these are the subtypes. Like we have int 8, we have int 16, we have int 32, and we have int 64, and the particular ranges, which is being calculated by the formula which we have discussed. So for int 8, the minimum value which we can store is minus 128, whereas the maximum value is 127. And if I try to change this int to int 8, and if I try to store a value which is larger than this, like for example 128, you can see that our compiler starts complaining, telling that you cannot use 128 as int 8 value in variable declaration. Why? Because it overflows, and if you run this, you can see that you'll get an error. Okay, so which is not right. So compiler is not accepting it. So what we have to do, based on the range, based on the value which we want to store, we have to change the data type. Like, now this falls into this category, right? So I can change it to int 8 to int 16. And now if I try to make this as int 16, you can run the program and you can see the output as 128. Okay, so based on the ranges, you can use the subtypes. Okay, we do even have the same subtypes in unsigned integers also. Okay, simply what you can say is, you can just say this is an unsigned integer, and it works in the same way. You can see that we have printed 128 over here. And if you try to store a negative value into it, what happens? It starts complaining. Same thing again. We'll get the same error, overflows. Okay, so just try to change this. So that's about signed and unsigned integers and the subtypes. So these subtypes are very much handy when it comes to like developers. See, basically developers, or they can create boundaries for the variables by using these subtypes. Okay, and for unsigned integers, the range formula differs. It becomes like 0 to 2 power n minus 1. Using this formula, you can calculate the minimum value and the maximum value. Simply, the minimum value is 0 always. Okay, you can just calculate the maximum value using this formula. So that is what unsigned integers are. And one more thing, a trip. So choose the smallest size possible. Why? Because for memory optimization, always use the smallest integer type that fits your data. Okay, so that's about integers. And one more thing, use signed integers if you need both negative and positive values, and prefer unsigned integers for IDs or indexes. Okay, always match your data range with appropriate integer type to avoid memory waste. And one more thing, see, if I don't want this headache, I can just say this as int. Okay, I can store any value in it, and the value changes, the data type changes into a default thing. Like for example, the compiler defaultly makes this as int 64 based on your machine. Okay, if you want to, we can check that one. How we can do is, I'll show you this. We have a package called as unsafe. Okay, and we have a function called a size of, and if you give a value to it, and by default this int is converted into int 32 or int 64 based on your machine's architecture. Okay, if you are using a 32-bit system, it will be of int 32, or if you are using a 64-bit system, it will change into int 64 by default. Okay, so int 64. And now if I try to print this, you can see that it is storing 8 bytes of memory. And even if I remove the 64 and if I just run for integer, we'll get the same output, because by default it is using int 64. Okay, so that is how we store integer values in our variables. Okay, and based on your preferences, based on your ranges, you can change this subtypes also. That's about our integers. And now comes the floating point. See, floating points handle numbers with the decimals. So if your number has a decimal, then you have to use floating points. And these are represented using IEEE 754 standard. And even we do have some two different types of floating points, that is float 32 and float 64. So float 32 is for single precision and float 64 is for double precision. Now let us see that one also. Let me change this to float 32, and if I try to store a smaller value into it with the decimals, and if I try to print this, Let me run this. And it is using 4 bytes of your computer memory. Okay. So this is occupying 4 bytes of memory. And if you just try to print A, and now you can see if you run this program, unsafe imported, sorry, let me remove this. And if you run this program again, you can see that we have printed 128.3456. And if you try to store a larger value into it, okay, and if you run this program, you can see that it has sliced it, okay, which is not good. In that scenario, you have to use 64, float 64 is what you have to use. And if you try to print this, the whole value gets printed, okay. And one more thing, if your like the precision is about 6 to 7 decimal digits, like after point, if you're trying to store 6 to 7 decimal digits, it is better to use float 32. And if you have almost 15 to 16 decimal digits of after the point, it is better to use float 64. Okay, so that is like it is based completely on the precision. And one more thing, always use float 64 for higher precision, okay, because you might get many errors if you are using float 32. And now that's about integers and floating point numbers. Simply, if you want to store numbers, we have integers, and if you want to store numbers with decimal points, we have float. And it is always better to use float 64. And when it comes to integers, it is better to use int. And if you are particular with your memory resources, then you have to choose these subtypes, okay. And the existence of subtypes in integers and floats is primarily for efficiency, precision, and flexibility in programming. So let's break it down. Like, why do we need these subtypes? Like int 8, int 16, int 32. Why do we need this? Simply, the first reason would be like memory optimization. So each integer or float subtype uses a specific number of bits, allowing developers to choose a type based on the range of values they expect. So if you know you only need numbers between 0 to 255, you can use uint8, which takes only 1 byte of your memory. Okay, and it is more memory efficient than int64. So by default, if you are storing int, instead of that, if you know that you'll be storing only 0 to 255, it is always better to choose uint8. Okay, why should we go for int64? Why we have to take lots of memory when you can use a smaller memory thing? Okay, so efficient use of memory is critical in applications where resources are limited. Like for example, if you're dealing with embedded systems or IoT devices, you have to be very particular with this memory usage. So that's the reason why do we need these subtypes. And we have the second reason, performance improvement. So smaller types always they can be processed faster by the CPU compared to the large types. So int8 or uint8 can be processed faster than int64 or float 64. Okay, so operations on smaller data types often require fewer CPU cycles. So in high performance applications, like if you are trying to build some gaming applications or scientific simulations, even a small optimization can make a big difference. Okay, so that is where these subtypes will become more handy. And you can prevent overflow and errors. So subtypes help programmers set clear boundaries for the values a variable can hold, reducing the chances of unexpected overflow or underflow. So if you're trying to store a value which is larger than 255, what you can do is you can use a different subtype. So based on the value you are storing, as per your knowledge, you can use these subtypes. And choosing the right subtype can prevent any kind of errors. Okay. And flexibility and specificity. So subtypes gives developers the flexibility to pick the type that best fits the needs. For example, you can use uint8 for small counters, or if you are using larger ranges like for timestamps or unique IDs, you can go for int64. So subtypes exist to strike a balance between memory usage, performance, precision, and flexibility. So by providing a range of types, Go allows developers to write efficient, robust, and scalable programs tailored to their specific needs. So that's about our integers and floating points. So simply to conclude, if you are storing numbers, you can go with int. And if you are particular about the value ranges, like if you want to save lots of memory, you can go with subtypes like int 8, and you can see the ranges over here. So based on these ranges, you can choose that particular subtype. Okay. And now comes strings. So what is this string? So strings are nothing but sequences of characters enclosed in double quotes. For example, I want to store a name. Okay, I can just say that name, which is of type string, and I'll just store Ishwa. And if I try to print this, you can see the output as Ishwa. So simply strings are nothing but sequence of characters which are enclosed in double quotes, and they are immutable, meaning once if you create a string, they cannot be changed directly. Okay, so that's about our strings. And if you want to check how much size they are taking, like how much memory they are occupying, means simply same thing again. So unsafe dot unsafe dot size of, and you can just say the name. And if you run this program, you can see the output as 16 bytes of memory is being occupied by strings. Okay, so that is how you can check how much memory is getting occupied by these, like the variables. So that's about our strings. And finally comes the booleans. So booleans represent true or false values, making them ideal for conditions or toggles. Okay, it is mainly used for decision making. Suppose if you want to print a particular message for a specific condition, and if the condition fails, you want to print out a different kind of message. So where decision making is mandatory, in such cases we can use this booleans. We only have two values, one is true, another one is false. Let me change this. Like for example, I'll change this to bool, and I'll just store true. Okay, and if I try to check how much memory is being occupied by this boolean, if I run this program, you can see that 1 byte, it only takes 1 byte to store booleans. Okay, so using booleans to optimize decision making is always a good thing in your code. Okay, so that's about booleans. You can either store true or you can either store false. Okay, only two values. So that's about our basic data types. Like we have numbers, we have floating points, like sorry, we have integers, we have floating points, we have strings, and we have booleans. Okay, and based on your preferences, you can choose your particular data type. And let's bring it all together with some real world examples. Okay, so think about counting the number of users in an application. In such cases, we have to use integers for counts or IDs. And if you're trying to store financial data like bank balances, you can use floating points. And if you're trying to store names, addresses, or messages, in such cases, strings become more handy. And finally, if you're trying to like build a dark mode switch, features like toggling features in an application, you can go for booleans. Okay, so that is how we can use these data types in our programs based on our requirement. And that's a wrap on episode 9. So now we have all the tools and tricks to handle Golang data types like a pro. So try experimenting with different types and subtypes to see their behavior in action. And don't forget to like, share, and subscribe for more exciting episodes. Until next time, keep grappling with code, and bye bye.